Hello and welcome to my talk. I would like to present some joint work together with Daniel Rudolph from Göttingen, and we were investigating a particular Metropolis-Hastings importance sampling estimator. The basic idea of this estimator is that instead of using only the accepted states generated in the Metropolis-Hastings algorithm, we are now basing this estimator on the potentially less correlated proposed states within the algorithm, and we will present some interesting theoretical results in this talk, as well as some numerical evidence when this new estimator can indeed outperform the classical path average estimator. But before we go into details, let me first introduce the main motivation and the main setting in this talk. So as usual, we would like to compute expectations of quantities of interest or functions f defined on a measurable set G, taking real values. And we would like to compute expectations with respect to a certain target or posterior probability measure mu on G, which itself is given via an unnormalized density pi of x, which is a density with respect to a reference or prior probability measure in the Bayesian setting. This reference measure will be denoted by mu0, and the usual approach in Markov chain Monte Carlo methods is then to construct a Markov chain denoted by xk here, such that this Markov chain has mu as its invariant measure, and then to approximate the desired expectation of f with respect to mu by this path average of f evaluated at the states of the Markov chain. This classical path average estimator will be denoted by Sn of f, n denoting here the number of samples taken into account. Now in this talk we focus on Markov chains generated by the Metropolis-Hastings algorithm, and as a quick reminder how this algorithm works, it generates a mu invariant Markov chain by a two-step procedure. In the first step, given the current state being xk, we use a so-called proposal kernel, so a probability measure depending on the current state of the Markov chain, and draw a sample yk of this random variable capital Yk, which is distributed according to p of xk. But this proposed new state yk is only accepted with a certain probability alpha of xk and yk, so there is usually a positive rejection probability and a probability that the next state of the Markov chain is simply the current one. Now, throughout the talk, we will make the following basic assumption about our proposal kernel P. We assume that for any state x in the measurable set G, there exists a proposal density of the corresponding proposal kernel evaluated at x with respect to our reference or prior measure mu0, and this proposal density has to satisfy the following condition stated here. So whenever the target density has a value greater than 0 for y, so does the proposal density at x and y. This basically means that the support of the proposal kernel evaluated at x always includes the support of the target distribution pi or mu. Given this basic assumption, we have some very nice results for the path average estimator. In particular, this assumption on the proposal kernel ensures the Harris recurrence of the Markov chain generated by the Metropolis-Hastings algorithm, which we will call Metropolis-Hastings Markov chain. And this Harris recurrence itself yields then to a strong law of large numbers for our path average estimator Sn, meaning that the estimator converges almost surely to the desired expectation for absolutely integrable quantities of interest f with real values. A measure of efficiency for the path average estimator is then, under this Harris recurrence assumption, provided by a central limit theorem. So if we start in stationarity and if we assume that the asymptotic variance here is finite, then the error between the path average estimator and true expectation scaled with the square root of number of samples converges in this distribution to a mean zero Gaussian distribution with this asymptotic variance. Now let's take a look at this variance. It includes naturally also the variance of f with respect to mu, but then we also have here this additional term of the summed up or integrated covariances of f evaluated at the different states of the Markov chain, meaning that the high order correlation usually yields to a high asymptotic variance of the path average estimator and therefore to a smaller statistical efficiency. Now this fact that the correlation of the accepted states plays a role in the statistical efficiency of this estimator serves now as a motivation for a new estimator based on the proposed states. We have already discussed that this high order correlation decreases the statistical efficiency, and one significant reason for autocorrelation in Metropolis-Hastings Markov chains is of course the rejection of the proposed states. For instance, if you recall that for random walk-like proposals the usual rule of thumb is to have an average acceptance rate of 23–25%, meaning that you have an average rejection rate of 75%, you see that the autocorrelation due to rejection is a significant thing. Now, since besides these accepted states we also have the proposed new states, which are potentially less correlated since there is no rejection step involved in the generation of these YKs, why not considering an estimator which evaluates f now at the proposed instead of the accepted states xk? Of course, in order to achieve consistency then of this average, weighted average here, of f evaluated at yk, we have to use appropriate weights wk, since the distribution of yk is usually not mu, and also the invariant distribution of these yks is usually not mu. So there are different ways to define such estimators using only these proposed states, and in this talk we will focus on the following Metropolis-Hastings importance sampling estimator. This estimator now employs the so-called augmented Markov chain, which consists of the accepted as well as the proposed states yk, and the estimator looks like this. So it's like a self-normalized importance sampling estimator. We evaluate f here at yk, and then we have here the corresponding unnormalized weights given by the value of this function pi bar evaluated at xk and yk, and pi bar is given as the ratio of the unnormalized density of our target distribution divided by the proposal distribution. This ratio is well defined due to our basic assumption on the proposal kernel, and this pi bar also plays the role of the unnormalized importance weight of this importance distribution, which is now given by the proposal kernel evaluated at the current state xk with respect to the target distribution. So this Metropolis-Hastings importance sampling estimator can be thought of in two different ways. One way would be that we have an importance weighted correction of these proposed states generated by the Markov chain. Another way to look at it would be that we have an importance sampling estimator where the importance distribution is provided by the proposal kernel of a Metropolis-Hastings algorithm and an underlying Markov chain xk. And these two ways are always helpful when analyzing this algorithm. So I would also like to present now our first theoretical result concerning this new estimator based on the augmented Markov chain, which tells us that this is indeed a consistent estimator. This theorem will state a strong law of large numbers of this new estimator under quite mild assumptions, namely the same assumptions which we had basically for the path average estimator, that the Markov chain generated by the Metropolis-Hastings algorithm is Harris recurrent. Under this assumption we can also prove that then also the augmented Markov chain is Harris recurrent, and this fact can again be used to derive the strong law of large numbers for this Metropolis-Hastings importance sampling estimator, which now also converges almost surely to the desired expectation of f with respect to mu for absolutely integrable quantities of interest. So this theorem states that this is indeed a reasonable estimator which does its job, but how about a measure for efficiency for this new estimator? Can we derive also a central limit theorem, and if so, what's the asymptotic variance of this estimator? To this end, we have proven the following theorem, which has again the same mild assumption of Harris recurrence of the underlying Metropolis-Hastings Markov chain, and as usual, the assumption that we start in stationarity. Then for any square integrable function f, we can prove that the error between this new estimator and the true expectation scaled with the number of samples, square root of samples, converges in distribution again to a mean zero normal distribution where the asymptotic variance is given now by this formula here. Here we have an explicit expression given by this double integral, so we integrate with respect to y using here the proposal kernel, and then we also integrate with respect to the states x with respect to the target probability distribution mu, and here inside we have the squared derivation of f from its expectation evaluated at y, as well as the square of the now normalized weight distribution or weight function for these importance sampling estimator. So in fact we notice that first of all there's no autocorrelation term involved in this asymptotic variance for the new estimator, and second of all the asymptotic variance coincides with the asymptotic variance of a self-normalizing importance sampling estimator, which would use independent pairs xk, yk distributed according to the asymptotic distribution of this pair. So x is distributed according to mu and y conditioned on x is distributed according to the proposal kernel. So this is in fact the invariant measure for the augmented Markov chain. And so there are two really surprising facts here for the asymptotic variance of this estimator. There's no autocorrelation, and in fact this asymptotic variance is the asymptotic variance of an importance sampling estimator using independent pairs, whereas in practice these pairs are of course correlated when we use the Metropolis-Hastings algorithm for constructing our Markov chain. Moreover, this explicit expression for the asymptotic variance allows now for an optimal tuning of, for example, the proposal variance in the Metropolis-Hastings algorithm. Usually in Markov chain Monte Carlo you have a proposal kernel like the Gaussian random walk proposal, where you have here a parameter s squared which steers the proposal variance or the step size of this random walk. And you usually choose S in such a way that you achieve a certain acceptance rate, the already mentioned 23–25%, in order to achieve best performance with respect to the path average estimator. Now for this Metropolis-Hastings importance sampling estimator, you can derive also an optimal tuning rule by deriving actually derivating this asymptotic variance with respect to S, and this yields to the following rule: if S squared is equal to this ratio of these expectations here, where we have again the squared deviation from f from its mean. Here we have the squared weight function again, now the unnormalized weight function. Here the squared step size of the proposal, and in the denominator we have here again same expectation as above without this squared step size times the dimension of the state space. If we choose S such that it equals this ratio, then we can prove that it has that the resulting Metropolis-Hastings importance sampling estimator has the smallest possible asymptotic variance, and for practical purposes these expectations here can of course be estimated again by path averages. So this optimal tuning rule can be implemented in practice and will usually yield to different step sizes or different proposal variances than the usual tuning rules for the path average estimator. We will illustrate this fact later with some numerical examples. But before we go to the numerical experiments, I would like to mention also some related work. Of course, we were not the first to think about estimators using the proposed states in the Metropolis-Hastings algorithm. A very similar estimator to our AN already appeared in a paper by Casella and Robert in 1996, but without any analysis, without proving consistency or analyzing the asymptotic variance. A similar idea is the idea by Frankel of waste recycling, where you use the values of f evaluated at the acceptance states as well as at the proposed states in this convex combination here. It was also later studied by Delmar and Jourdain. And also closely related to our estimator is a Markov chain importance sampling estimator developed by Klebanov and Schuster, which also uses self-normalized importance sampling estimators, but based now on a different distribution of these yk, namely the asymptotic distributions of these proposed states yk, which is given here by this density qy. So here we have the integral of the proposal density with respect to mu0 integrated with respect to the invariant measure of the states of the Markov chain. And this density could again be in practice be estimated by path averages, so evaluating this proposal density at the current states of the Markov chain. And now we will come to the numerical experiments, and we will verify in which cases this new estimator based on the proposed states might indeed outperform the classical path average estimator, and in which situations the path average estimator actually has a better performance than this new estimator. But we will also compare our estimator to the previously mentioned alternatives, the waste recycling estimator, as well as the estimator developed by Klebanov and Schuster, which takes a very similar form to ours, just the weights are now computed as explained on the previous slide in this different way, where you have here the asymptotic variance of the proposals and not the proposal density fixed for the particular xk. Now, this estimator by Klebanov and Schuster has a higher complexity, computational complexity than the other estimators. In fact, due to this extra summation here for the computation of the weights, you have a complexity of n squared, whereas the other estimators all have a complexity of O of n. And therefore, we will consider in the numerical experiments also b of square root of n for a fair comparison, taking into account the higher computational complexity of Bn. Now, in the first experiment, we investigate, or we apply some Bayesian inference for an ordinary differential equation model, where we would like to infer two coefficients in the model based on noisy observations of the solution. The state space here is r squared, and the results for computing the posterior expectation are shown here. So we employ a Gaussian random walk proposal as well as the Mahler algorithm, and we compute the usual path average estimator as well as our importance sampling based estimator for various step sizes or various average acceptance rates in the Metropolis-Hastings algorithm. On the y-axis you can see here the root mean squared error, and in both cases our new estimator can achieve a significantly reduced error, which is in fact just half the size of the error of the classical path average estimator for a particular optimal tuning. So if you choose here the correct optimal tuning for our new estimator, you can achieve a significant error reduction for the same computational cost as was required for computing the path average estimator, because these additional densities pi bar required for AN only involve terms which are also required for the acceptance probability in the Metropolis-Hastings algorithm. So except for this self-normalizing step, there's really no additional computational work for computing AN compared to SN. So we see here that for optimal tuning, this new estimator can indeed outperform the classical one. How does it perform in comparison to the other alternatives? So in these plots, you see the results also for waste recycling given by the purple line, which in these experiments actually coincides pretty much with the errors obtained by the path average estimator. You also see by yellow and green the results obtained by the estimator by Klebanov and Schuster for Bn and B square root of n. You see that this Bn estimator, which uses the asymptotic variance of the proposals, can achieve even smaller errors than our simple Metropolis-Hastings importance sampling estimator. And also the optimal tuning is again a different one for this Bn estimator. It is roughly here 60 or 65% in both cases. However, if you take into account the extra computational work required for computing Bn, so if you take a look at B square root of n, you see that unfortunately you would achieve much higher errors also compared to this path average estimator for the same computational work. Okay, in a second numerical experiment, we are considering Bayesian Probit regression for the PIMA dataset. And here we wanted to investigate how these Metropolis-Hastings importance sampling estimators perform with respect to an increasing dimension of the state space. So we varied the number of regressors from 3 to 9. And you can see here the results for 3 regressors, so state space is R3, that again, with an optimal tuning, you can achieve much smaller asymptotic variances when using these importance sampling based estimators using the less correlated proposals. Again, you can use here the tuning rule to find the optimal tuning for AN, and for BN, again, you would have a different optimal tuning, which appears here to be a roughly 60% error acceptance rate, but also if you consider B square root of n, you would achieve again significantly higher errors than the path average estimator. Waste recycling again coincided with the results for Sn. But if we take a look now at the higher dimensional problem, so d equals 9, we observe that our simple Metropolis-Hastings importance sampling estimator unfortunately could not outperform the classical path average, since even with the optimal tuning, the minimal variance was significantly higher than the minimal variance obtained by the optimally tuned Metropolis-Hastings path average estimator. Bn here could achieve smaller errors than the path average estimator, but the improvement was already smaller than in the case of 3 dimensions. So actually both importance sampling based improvements, or both importance sampling based estimators AN and BN, they show a vanishing improvement over the classical estimator for higher dimensions. So if we would increase the dimension further to maybe 20 or 30, also Bn would have higher variances than the optimally tuned path average estimator. So to summarize my talk, we have analyzed a particular estimator which was based on the proposed states in the Metropolis-Hastings algorithm, and we used some importance sampling reweighting in order to achieve consistency of this particular estimator. In fact, we were able to prove a strong law of large numbers as well as a central limit theorem for this estimator under rather mild assumptions. And surprisingly, the asymptotic variance of this new estimator included no correlation terms and corresponded to an importance sampling asymptotic variance for independent samples. Moreover, the explicit formula for this asymptotic variance allowed for deriving optimal tuning rules which could be implemented in practice, and we have investigated in numerical examples in which cases this alternative estimator based on the proposed states could outperform the classical path average estimator for the same cost, but this happens to be only the case in rather small dimensional state spaces, so up to dimension 5 in our numerical experiments. So I would like to thank you for your attention, and if you are interested in more details about this Metropolis-Hastings estimator, then I would like to refer you to our published work here in the Electronic Journal of Statistics, and here you have also the other references for the other alternative approaches to the classical path average estimator. So thank you for your attention and goodbye.